So you'll notice on this problem, you probably didn't get the answer I got, and that's because I grabbed the specific heat of iron instead of the specific heat of lead. So if you change it just a little bit, have this little improvement here. So you'll notice that putting in 0.128 rather than the number I gave you will absolutely give you 1.5 joules per gram degree Celsius. Pause and try these on your own first. You'll notice on this problem I made some notations beforehand. That's great. You can do that or make the list on the side. For our mass of our metal, there's a big hint. It says it's submerged in boiling water, and we know boiling water is 100 degrees Celsius. This isn't the heat exchange we're talking about. So the boiling water submerged, it's the initial temperature of the metal. They're getting the metal to 100 degrees because then it says, then it's transferred into some water. So I know it seems like there's two transferings going on, but that's what it's for. So we have 59.7 degrees. We don't know our C of our metal. Our final temperatures at the end, there's 279.75 Kelvin. And as you saw before, 100 Celsius is the same as 373 Kelvin. Since everything in here is Kelvin, we might as well have this in as Kelvin. Again, I like to have the chart all the way filled out before doing the math, so I'm going to wait on plugging that into my calculator. I'm going to move on. My mass of water is listed in milliliters, but remember 1 milliliter is equal to 1 gram for water. So I'm converting that like that. Notice that my specific heat is 4.184 joules per gram degree Celsius. Remember, this is not going to be given in the problem to you. Now my temperature T final minus T initial. The final is the 279.75. The initial is the 273.15. Notice that I have these labeled kind of strangely in the problem. I have it reversed with the labeling, but I have it correct here in the math. So when I do my subtraction, I get 6.60. That's one position. And then when I do the other subtraction, I get 93.4. Just want to note, because it says it's water at 273.15, it's already gone through the phase change from being ice, and it just is at the coldest state that water could be in at 273.15, if you were wondering about that. So we have 59.7 grams times C times negative 93.4 equals, we have our 60.0 grams times our 4.184, and then we have times our 6.60. I need to make sure that we divide both sides so that our red C is by itself. Notice that I forgot my negative when I started filling this out. Can't forget it. Make sure you're canceling what's on the same, and I get C is equal to 0.268 joules per gram degrees Celsius. Now we're going to look at our very last example problem. Since you're working these on your own ahead of time, I'm pretty sure you will have all of these numbers ready. Make sure you've got the correct final and initial values for your temperature. Remember that the 42.7, they both come to that temperature. I want to point out something going on right here. When we do this subtraction, it is going to turn out to only have 2 sig figs. So it's 18.7, but we round it to the 24 position. That gives us 19. However, we're about to do a lot of math, and I don't want to lose anything. Remember, you're only supposed to round once. So we're keeping in mind that we are going to be limited by 2 sig figs, but we're going to put the full 18.7 into the problem so we don't end up with any rounding errors. The other times that we've subtracted and ended up with 2 sig figs, we wouldn't have had a rounding error because that last number was a 0. So for the math purposes, it's not a huge difference between 8.30 and 8.3. In this case, there's an actual number there, could make a difference. So we're going to fill in our typical equation. 360.0 grams times 0.449 joules per grams degrees Celsius times, we're going to call this delta T. We could put the numbers in, but this is so much easier this way. And I dropped the negative, so there you go. There's the negative. So now we've got a 425 times 4.184 times, and we're going to write down the 18.7, but knowing that that should be 2 sig figs. So I'm going to get that delta T by itself by dividing both sides by, don't forget the negative, 360.0 grams and the 0.449. Notice they both cancel. I'm putting it all on this side. I probably should have waited to cancel until I got everything to the other side. Don't forget the negative. And I should get that delta T is negative 205.7. If you go back and work the problem without that negative, you're going to end up with a ridiculous temperature saying that your metal is colder than the water you put it in, which doesn't make any sense because it was hot. So we have our final, which is the 42.7 minus our initial, is equal to the negative 205.7. Be careful with your negatives here. You're going to subtract 42.7 from both sides, and you're going to get rid of the left 42.7. You'll end up with negative TI is equal to 247.7. Don't forget that that's negative. So now you can divide both sides by a negative and get TI equals 247.7 degrees Celsius. And this answer does make sense. It's a very hot temperature. It makes sense that it would make the water's temperature rise from its initial value quite a bit. So let's see how our sig figs affected things. So my delta T answer would have been to 2 sig figs, which would have been like negative 210. That's too much rounding because, again, we're not done with the problem. But I'm remembering that it goes into the tenths place. And so my final answer is going to need to be rounded into the tenths place, and it's going to be 250. And there shouldn't be a 0.0, it's just 250. You're done with this part of the chapter.